Today I have something pretty interesting for you. We're going to talk a little bit about all those digital images you look at on the internet or from your digital camera. And if you think about it, all those images, really they have to become a group of numbers. That's the only way your computer actually works. So you don't think about it like that, but they actually are just a set of numbers. And not only that, but they have fancy ways of making these files smaller, because the truth is, if you just did it naively, the files would be very, very large. And I actually brought some images with me to show you what I'm talking about. And I'll show you a little bit of the clever math involved in making these file sizes smaller so we can actually deal with them. So for example, I have a full resolution photo on my laptop. Our photographic model, by the way, is Miss Pickles. And Miss Pickles here is at full resolution, meaning what's happening here. And in fact, actually watch, if I zoom in here, you can start to see individual pixels. So as we get closer and closer, you're going to see individual blocks of color. And each block is one solid color. And when you make those small enough, the image looks really, really good. Well, this image right now is creating a number for each and every pixel to number the color. And basically what they do is they have a red, green, and a blue, 3 different color channels, and they assign a number between 0 and 255 to each one, and they have to record that for each and every pixel. I know this image didn't look very big, but there are thousands and thousands of pixels in just that image. So this creates quite a large file size. And actually this image isn't very big, but this is about 750 kilobytes, almost a megabyte for that small image. But I'm going to show you a JPEG image, which I bet you could not even tell the difference if you looked at it. So here's the original one again. This is the full resolution, and I just switched it to the JPEG. I bet you can't even tell. I know your TV isn't the best viewing medium, right? But even on my computer screen, I can't tell. And this image is 3.7 times smaller. This is about 200 kilobytes. And with JPEGs, you can actually adjust the quality level. So here's another JPEG that's even smaller file size. This one, I wrote these down, is 8 times smaller, and I still really can't tell the difference. Here's the next one. This one is 10 times smaller, and I'm starting to see just a little bit of choppiness, and it's not quite as good. I kept decreasing the quality, though. This one is actually 12 times smaller, and again, I'm seeing a little bit of quality go down here. And I did one more. This was the lowest quality setting I could choose to convert it to a JPEG. This one is 15 times smaller, and there are actually some issues with this one. I don't know if you can tell on your TV screen, but I'm going to zoom into it a little bit. You'll start seeing blocks of color. In fact, you'll see sort of strange squarish patterns in the image there. So this is what JPEG is doing. So how does this work? I mean, how is it creating a file that's a lot smaller but actually still looks pretty decent? They've done some clever things. First of all, what they do is they take this image and they cut it up into blocks of 8 by 8 pixels. So as a sample, I've drawn a grid over this image, and that's the idea. They break it up in lots of little tiny chunks. Here is one of those blocks. I've blown it up for you. This is 8 by 8, so that's 64 individual pixels. You can see the individual colors, and they will turn this into a matrix of numbers. So actually what they do is they split this to 3 channels, and they don't just use red, green, and blue. They found out it's actually more efficient to split one channel just for the brightness of each pixel, and then 2 other channels that control the color. So one thing they do, for example, is they've studied that the human eye is much more perceptive on the brightness variations than it is on the individual colors. So they can actually average out the colors a little bit. So for instance, they could say, well, we're just going to take the color for every 4 pixels. We'll kind of round them off that way. And you can actually make the file 50% smaller that way, and most people can't even detect it at all. But we'll retain most of the brightness information. So for each of those 3 channels, we'll have these separate grids of numbers controlling those. And I'll show you what it looks like. It's basically a matrix of 64 numbers, and each of those numbers represents one of the color or brightness values. But this still is a lot of information to encode. So after that, they take this matrix of numbers, and they change how this is expressed. And they use something fancy called the discrete cosine transform. I know it sounds fancy. You don't need to worry about what it is. I'll show you its equation, though, so it'll look official, right? So here's the equation for you. What this is doing is it is basically creating a different expression for that matrix. And what it does is it takes a whole bunch of different cosine graphs. Now, I've shown you, these are 3D cosine graphs, and there's 64 different possibilities. I'm showing you a sampling here. And basically what they do is they add different ones of these together to create that grid of numbers or the level of colors. So for instance, this one you see in the bottom right corner is very choppy up and down. That would represent a lot of color variation in one little block. Most of the blocks that's not necessary. So for example, up top you see ones that just have a little bit of change. I'll give you a 2D version. This is all 64 blocks here And the differences are measured in brightness, and you see in the upper left there's just a solid white, and then there's some look kind of striped, and there's some look almost like checkerboard. So the idea is you would look at the color variation and the brightness variation on your block, and you would just take the appropriate ones of these to add them together, and you'll create something very close to the original. So once they do this, you're going to create a new grid of numbers, and to make it even smaller file, this is already a more efficient way to express the color variations, but to make it an even smaller file, what they do is they divide the numbers by something larger to make them all smaller, and then they round them off. So it's almost like saying if you have numbers from 0 to 255, we're going to take them and cut them down to only go to, say, 0 to 30, and we're going to round off the extras. So what that does, it kind of makes the colors rounded off a little bit, and it makes fewer things to keep track of. But then they're even more clever, because if you look at this matrix, most of the numbers rounded off to 0. And in fact, there's some logic to this. In the upper left corner, you see a -26. That represents the average brightness level for this block. And then the numbers you see after that are how far they vary from there. So rather than giving the level for every single one, you just say, hey, on the average, they're -26, and the next one's 3 down from there, and the next one's 6 down from there. You get a lot smaller number to keep track of. And then they have one last clever trick. See all those zeros? When they list it in the computer file, they don't bother to say 0, 0, 0, 0, 0 over and over. They just say, hey, there's 45 zeros at the end. And there's a computer way of saying, make 0 happen 45 times, which is a lot smaller than actually saying 0, 0, 0, 0, 0. So when all is said and done, you can actually get a JPEG image that's about 9 times smaller that will look very good. In fact, it would be hard to tell. If you stared at it really close, you might be able to tell, but it would be hard to tell from the original image. So keep that in mind. Next time you open up an image, and I have one more sample with me, you double-click on an image. It's a stream of numbers in your computer. Your computer opens the stream of numbers. It runs some mathematical algorithms to reverse all those processes we just discussed. And then it comes up with an image like this. Now, this is the full-size one. This is the JPEG version. You probably couldn't even tell I changed it. This is 7.5 times smaller file. It looks just as good to me. Probably does to you on your TV screen. And just for comparison, I put a low-quality JPEG version on here. This one is 16 times smaller, the file. It's a very small file. It probably still looks okay, but if I zoom into it, you will see some choppiness. In fact, if you look at the bird's feathers and the beak there, you will start seeing some weird patterns in the blocks it's formed. But still, it's not bad. And keep in mind, every time you look at images, your computer is taking these numbers and undoing all these processes with algorithms. And if it weren't, in fact, if you have a digital camera right now, it's likely that it saves in JPEG format. Most of them do by default. If it didn't, that little memory card you have in there would hold a handful of photos and not the hundreds or thousands that it actually does. So next time you open an image, keep this in mind. Underneath there, it's all numbers and math, just like movies on your computer and MP3s on your computer and your iPod and everything else. But we'll get to those another time. All right. So anyway, I hope you find that interesting. Next time you open up an image, keep all that in mind. Hey, it's Mathman Dan. We are driving around the northeast part of San Diego County. We're doing some filming around here, but now we are lost. Luckily though, I brought a GPS with me, and if I just push a few buttons on this thing, it's going to tell me exactly how to get home. So how does this thing work? I mean, I know that it has the maps programmed in it, so that's one thing, but the main reason this thing can work for me is it knows exactly where I am. Well, it turns out that this little device has to do a lot of math to make that happen. And you might have heard that it talks to satellites to get its location. Well, that's sort of true, but this thing's not sending a signal to the satellites and asking, hey, where am I? And then listening for the response. In fact, this thing doesn't transmit anything to the satellites. The truth is there are 24 satellites orbiting the globe, and they are all transmitting signals that this thing can listen to. But first, all those satellites have to be synchronized. So they all have atomic clocks. They're precisely synchronized to be the same time. And with some mathematical tricks, this thing can figure out what that exact time is, so it can synchronize itself also. Then each satellite transmits a signal of numbers generated by a formula. This is programmed with the same formulas, so it knows what numbers are coming down from each satellite at precisely what time. By looking at the time it actually gets the signal, it knows how long each signal took to reach it. Well, since the signals travel at the speed of light, it can then compute how far away each satellite is from it. Well, there's one big mathematical problem left. If you just know the distance from a bunch of satellites, how do you figure out where you are on the planet, and how many satellites does it take? Because it turns out 1 is not enough, and in fact 2 isn't enough either. So back in the studio, I'm going to talk to you about exactly what math this thing has to do with these distances to figure out how exactly where we're moving and where we are on the planet so they can send us home safely. So back in the studio, I'll show you the mathematical tricks. In the meantime, this thing's going to get us home. You know, there's tons of math that went into getting that satellite system, up and running in the sky up there. But we're going to concentrate today on what that little device has to do to figure this all out for us. And I don't know about you guys, but that thing has saved me many times because, I don't know, I think I'm directionally impaired. Anyway, I brought in my GPS. It's on my math cam here. So I'm going to show you, for one thing, that it shows you what satellites it's actually monitoring. So here's a little map of where we are. I'm going to have it show me what satellites it's listening to. And you can see right now it's tracking 10 different satellites. And I mentioned when we were in the car there that 24 satellites are up in the sky. There's actually more than that. The system started with 24, but they have some extras for backups in case one of them fails. And they also have put some additional ones because the more they can get up there, then you get more information, you get redundant information that can help you get everything figured out quicker. But quite a bit of math this little guy has to do. First, a couple pictures though before I show you precisely what it's doing. Here's what a satellite looks like. That's an artist's rendition of roughly what they look like up in the sky. And also, this is a little animation of the satellites in separate orbits going around. And what I want you to watch is there's a spot on the Earth there in the middle, and these satellites are all in their own orbits, but it's made so that at any given time, at any point on the planet, you should be able to see at least 6 satellites. So, I mean, my GPS right now was getting 10, which is more than necessary. So one of the questions I asked was, how many do you need to actually make this happen? And, well, you don't need 6, you don't need 10. You can get away with fewer than that, but 1 or 2 is not enough as well either. So I promised I would show you a little math on how the device figures out where you are. And keep in mind, the GPS that you hold in your hand cannot communicate with the satellites. It's not sending anything. It has to just listen and somehow figure it all out. So as I mentioned, there's streams of data coming down. They have their clocks synchronized. And basically what happens is the handheld you have figures out how long the signal takes to get to it from each satellite, and then it figures out the distances. So the remaining question is, if you just know distances from a bunch of satellites around you, how do you figure out where exactly you are? And there's a lot of computations going on with the math, but I'm just going to show you some pictures because it's a little easier to explain that way. So first of all, what I have here, I have a little animation I've designed. So the blue thing in the middle, that dot, that's representing not the Earth, that's the satellite. And the yellow dot is you. And so if you have one satellite and you have a distance that you know, that means you could be anywhere around that satellite the same distance. And we're working in 3D here. So anywhere around there, you could be somewhere. If you only had one satellite, that's the best it could do. It could say, hey, you're hovering around me somewhere. So what we can do is I'm going to turn on a sphere here. And we can say, all right, you would have to be on the surface of that sphere. So the center of the sphere is the satellite, and the sphere represents all the different places you could be because you can roam around here any of these distances. So just one satellite, all I would know is, hey, I'm on this surface somewhere. We don't really know exactly where yet. Well, what if you had 2 satellites? So what I'm going to do is imagine that you have a measurement from one satellite. That means you're stuck on a certain sphere. And if you have another satellite somewhere else, then you can visualize being on 2 different spheres because those are distances from 2 different centers. And now think to yourself, okay, how could you be on both spheres at the same time? You would have to be on their intersection. So I'm going to show you their intersection in red. So you can see that little red stripe hopefully around the 2 spheres. That's a circle. Anytime you meet 2 spheres up, they're going to be intersecting in a circle. So if I turn the spheres off, what we have now is this red ring you see floating in the middle. You have to be on that ring somewhere. So 2 satellites tells you, hey, I'm on this ring somewhere, but that's still not enough to figure out where you are. What if we turn on a 3rd satellite? Okay, well now I can see that it's hitting the ring in 2 spots. So with 3 satellites, I actually have 2 different possible locations. So technically 3 satellites isn't even enough. You actually need 4 to pinpoint one precise location. So one last little illustration here. And now keep in mind, the device is not drawing these pictures like I am. The device is actually taking the equations of the 3 spheres, which it's doing, and it's solving a system basically and figuring out what points are in common of all the spheres and figuring out where you must be. So 4 satellites minimum to make this all happen. Remember, the system's designed so you can see at least 6. And the reason is extra satellites provide extra information. So one last illustration here. I have the Earth drawn. And we're going to imagine that you have satellites floating above you, and we're going to start turning on those spheres of where you could possibly be. So here's one, for instance, that would show you that on the surface of the Earth you're on some ring. Then let's turn on a second one. So now I can see that, well, I'd have to be on the intersection of those two things, and if you're on the surface of the Earth, then there's only a couple possibilities. Let's turn on a third one now. Now you can see that it's pinpointing a spot. I don't know if you can see my little pointer there. Right in the middle there, it looks like you're roughly in, I don't know, maybe about Tijuana, Mexico there. So that's 3 satellites. Now, if you consider the Earth itself as data, you can actually get away with 3. Because if you know you're on the surface of the Earth, then that's sort of counting as a sphere you have to be set on. That might not be true if you're out floating in space, right? And you can use GPSs anywhere. So if you don't account for the fact that, hey, I'm on the surface of the Earth or at a certain elevation, you really need 4 satellites to make it happen. And the reason 5 or 6 is even better is they can more quickly determine where you are, because unfortunately there are little errors that creep in, and your handheld GPS has to adjust for those. So really, the more satellites it gets, the better. So why would there be errors? I mean, these things are very accurate if you look at them. They get you within, I don't know, like a yard of where you really are. Maybe it's not quite that good, but I mean, they're very, very accurate. Well, the thing is, these signals, as I mentioned, are coming down at the speed of light. So try to imagine that it's timing these, and it's counting the split seconds, probably several decimal places of a second here of how much time it takes. And if it's just slightly off, the speed of light is so fast that a very small error in time measurement creates a huge error in distance measurement. And if your distance is off, then your calculations are going to come out and give you the wrong location. So by taking several different satellites and looking at all of them where they could possibly overlap and converge, they can actually adjust for errors. And that's also, by the way, how they adjust for making the times all synchronized, because if the times are all off, then it's all screwed up too. So anyway, very complicated process, but just think about all the math that little thing's doing. Next time you're driving around, is taking it for granted that, by sheer magic, it tells you where you're going, right? So today we actually have a little bit of mathematics in music. It turns out there is a lot of tie-in between mathematics and music. And I don't know if it's a coincidence or not, but a lot of mathematicians actually play musical instruments. There seems to be some correlation there. So to set the stage, and I will come back with some math after this, for a one-time only appearance, we assembled the official College Math Line band. We formed a band of only crew members of this program who just happened to be musicians. We got us all together one day and filmed an official College Math Line song for you. And the name of our band, of course, was Brutal Equation. So we'll come back to some math after this, all right? This is just to set the scenario for it. So enjoy the one-time recording of Brutal Equation, then we'll be back.
And algebra has got